Hola, mis estudiantes. All right, so we've already done a titration this year with methyl orange, and you guys got to experience the stress of that one less drop causing the overshooting of the color change between peach and watermelon. But now we're going to do a little bit more with the mathematics of acid-base reactions and some of the stoichiometry that comes from the balanced chemical equations that we have now mastered from previous lectures. So the terms volumetric analysis and titration pretty much are talking about the same thing. We have a known solution and we have an unknown solution. And we're going to control some volume being dispensed into the unknown solution until we get a volume from reading the burette. And that volume is going to allow us to kind of back calculate, using the BCE, the unknown solution concentration. So when I say unknown solution, you're talking about an analyte. When I say known solution, it's sometimes called the standardized solution. And that's going to be the one that we know the concentration of. These boxes means concentration. The equivalence point, which I have a star here representing the equivalence point, that's going to be when the moles of acid equals the moles of base. And if you look at your titration curve, it's the point where it's most up-down linear. Okay, so the curve turns into a straight line. Indicators, we've already messed with a couple of them. Phenolphthalein, I'm going to spell this wrong, I already know it. Phenolphthalein is one. Bromothionyl blue is another. Methyl red, methyl orange, azalean yellow. There's tons and tons of indicators, okay? They're all turn colors or change colors at different pHs because they have a specific weak acid within them that allows the color change to occur either maybe in acidic solutions, neutral solutions, or basic solutions. So we choose our indicator based on what we are titrating. The endpoint is where the indicator changes its color, going from the protonated to the deprotonated or vice versa of that weak acid. That's just a little known fact. We'll get into that a lot more when we get to acid-base equilibrium. And then the term standardizing solution is going to be on one of your labs coming up soon. And what that means is you're going to re-verify the solution that I've already made, and I may have actually told you the concentration already, but you're going to re-verify that with something that's a standardizing agent like KHP. This does not mean potassium hydrogen phosphorus. This is potassium hydrogen phthalate. It's a different chemical, and it's used for standardizing solutions, so you get the exact concentration of the titrant to make your stoichiometry more precise. This is just the general setup of a titration. We've used the burettes before. You've got your stopcock, and the perpendicular position is off, and then the parallel position is on. So something's going to be coming through and traveling through. You remember the burettes are listed in reverse order. So when you're reading them, you read them very carefully. And sometimes if you do need to, maybe there's splash marks on the side of your flask, and the burette is maybe touching the side of the flask, and you allow the drip to run down, you can actually rinse this with your DI water, because the DI water should be neutral and it shouldn't cause any changes to your pHs. Here's a graph showing you where different indicators change color. So the methyl orange changes from acidic to basic, from pink to kind of a peachy color at about 3 to 4 pH. But phenolphthalein doesn't change. It changes from colors to magenta pink at about 9 pH. So this is what I was telling you earlier, where different indicators are used for different reasons. All right, here's an example of a titration curve. And notice that this one is opposite than what we're generally used to. We're starting off basic, and we're going towards acidic. So the y-axis is pH, and the x-axis is the volume added of whatever your titrant is. So in this one, we have titration of sodium hydroxide of base with acid. So I might give you the title and I say, give me a sketch. So if I give you titration of HCl with sodium hydroxide, it's going to be our general sketch where you go from bottom to top. But in this one, we're going from top to bottom. And these are both, this is a strong base, and this is a strong acid. Since both of them are strong, you're going to have a neutral endpoint, which is endpoint of 7. Also the equivalence point, because since each of them are strong, they'll actually kind of negate each other. If it was maybe a weak base and a strong acid, then the strong acid wins, and so your equivalence point will be below 7. Opposite of that, if it was a strong base and a weak acid, then the strong base wins, and you're going to have a pH of above 7 for the equivalence point. So you can actually estimate these without having any information other than the two compounds being used. This region right here where it says buffer region, we're going to get into that a lot more, but a buffer region is where the pH is kind of limited in how much it changes. There's resistance to pH changes. Another type of system that we can talk about is a polyatomic, or a polyprotic system. So we have, obviously here we're starting acidic, so it means we have an acid being titrated with a base. So this information here is really important. This is a triprotic acid. The base is reacting with it. It's consuming all of the triprotic acid. So after this point right here, there's no more triprotic acid. There's only this diprotic acid. So as we continue, we get to this is the first equivalence point. We keep traveling. At the second equivalence point, there's been another certain amount of base added, so the OH here, added to totally consume all the extra or cause deprotonation of all the second H's coming off of this diprotic acid. So there's no more of this present here. We have all monoprotic acid. Okay, so then at the next equivalence point, there's actually not going to be another one, not here in this graph, but if we go a little further, there might be a curve upward and then back, where at this point there's been enough base added to negate the rest of the H from the monoprotic acid, leaving no more monoprotic acid and only the phosphate ion. So this is neat because you get to see the progression, and I might even ask you to draw the species present at the first equivalence point, the second equivalence point, and the third equivalence point, which is me right here. So if you could do that, you're awesome, but you might need to practice. All right, so let's do some math. The first thing here is a volume of 0.5 molar barium hydroxide will react completely with 25 mils of 0.2 molar hydrochloric acid. With these types of problems, usually the first thing you need to do is write your BCE and ID or identify your givens. And once you start with your givens, you're going to start canceling units in order to get to the unit of interest. Now, whenever you have an acid and base reaction, you're usually talking about molarities and volumes, but that's not moles. How do you get moles? You take M times V to give you moles, and then you can go further into your mole-mole ratio, which can get you something a little more usable. All right, what volume of 0.5 molar will react completely? Okay, so I'm going to stick with millimoles. I like millimoles. So 25.0 milliliters of solution times the molarity 0.200, and then I'm going to write this out for you. Millimoles of HCl per milliliter. All right, so now I'm in millimoles, which is essentially the same thing as moles. We're just using a smaller prefix here. So we have our BCE already written, maybe in our head. I'm going to write it down here now. Barium hydroxide plus HCl yields barium chloride and HOH. It's an acid-base neutralization reaction. There's 2 and 2, 2 and 2. Okay, so now I want to get to barium hydroxide, which means I need to go mole-mole ratio, where I've got 2 millimoles of HCl and 1 millimole of barium hydroxide. Okay, that question is asking for volume, which it doesn't specify milliliters or liters. Let's just do milliliters first. The last given that I've not used is the 0.5 molar, which means I need to put 1 milliliter on top and 0.500 millimoles of barium hydroxide down here. So far, the milliliters have canceled, the millimoles of HCl have canceled, and the millimoles of barium hydroxide has canceled. This leaves us with 5, let's see, sig figs here, 5.00 milliliters of the barium hydroxide solution. You could convert that to liters, but this works for me because most of the time our volumetric analysis questions require very small volumes. All right, next one. A 50 ml sample of ammonia solution is analyzed by titration with HCl. So we're starting with ammonia, we're adding HCl. The titration requires 39.47 mils of 0.0984 molar hydrochloric acid to reach the endpoint. The endpoint's where the moles are equal. What's the concentration of the ammonia solution? Okay, so first of all, let's get this BCE out of the way. HCl makes ammonium, and chloride ion. Okay, this is extremely relevant, but this part is where it's a 1-to-1 mole ratio. So the two things I'm given that are related to one another is the HCl volume and molarity. So remember, M times V equals moles is important here. It's usually always used. So 39.47 milliliters times 0.098 for millimoles. Starts to look like a squiggle after some time. Millimoles, and I'm going to put HCl up here so we remember, per 1 milliliter. So the milliliters are gone. Next thing we need to do is go ahead and get to the ammonia, which is 1 to 1 mole ratio. 1 millimole of NH3, 1 millimole of HCl. That's from our BCE here. So HCl millimoles are gone. Now our question, let's just re-look at it again one more time. Concentration, so we're looking for molarity. We have millimoles on top. If we divide by the 50 milliliter sample, then we will have molarity. Versus stopping here, calculating, and then dividing, I just like to multiply by the reciprocal, which is the same thing as dividing, which is 50.0 milliliters of NH3. That gives us 0.0776 6 molar. Okay, it's actually 6.7 molar. Let me rewrite that for you. 0.07767 molar NH3. Double check, we see 4 sig figs, 3 sig figs in some, so this right here needs to be rounded to 0.0777 molar. And that's our answer. So these are not too bad, it's just stoichiometry. Alright, this one's a little longer. Suppose that 5 grams of iron 3 oxide is added to 20 mils of 0.5 molar HCl. First, we need a BCE. So I'm going to write this down here because I think I'm going to write my before, during, and after, which I enjoy when we do limiting reagents. Since you're given as a mass of iron 3 oxide and some amount of HCl, you're given quantities of both reactants, and they don't tell you who's in excess. Therefore, you have to figure that out. So let's write this down here. Iron 3 oxide plus HCl yields iron 3 chloride plus water. And when you balance this out, you get 6 HCl's, 2 iron 3 chlorides, 3 waters. This iron 3 chloride is going to be our precipitate here, but that's not extremely important at this point. The question says, what is the concentration of F3 plus when all the HCl has been reacted? What mass of iron 3 oxide will not be reacted? So they kind of tell us our excess is iron 3 oxide. So I'm going to write that here. But, and you know, you could actually go through and do your math. You'd say 5 grams of this. And let's see, let's do millimoles, 20.0 milliliters of HCl times 0.500 molar. That gives us 10.0 millimoles of HCl. And for the 5 grams of iron 3 oxide, where we have 1 mole of iron 3 oxide, oops, that's a 2 there, and that's a 3 there, divided by the molar mass of that is 159.7 grams of iron 3 oxide. So this is going to give us some number of moles of iron 3 oxide, and we actually need to take that to millimoles since we want to be comparing similar units here. Okay, and that number is 31.3 millimoles. So I'll just scratch that out there for you. Okay, so comparing this number to this number, we can see that 10 divided by 6 is a smaller number than 31 divided by 1. So we were right. The limiting reagent is HCl and excess reagent is iron 3 oxide. So this is what we have before the reaction on both, and 0 and 0 on these two other products. During the reaction, we're minusing away the 10 millimoles of HCl and minusing 10 millimoles of HCl times the ratio of 1/6. And we're adding 10 millimoles and a ratio of 2/6 here, and adding 10 millimoles and a ratio of 3/6 here. So at the end of the reaction, when you take your 31.3 millimoles minusing your 10 millimoles, that's 21.3 millimoles of Fe2O3. We have 0 left of HCl. We have, let's see, 33.3. Alright, I had to pause that for a second. I had to fix a mistake I'd made. I forgot to multiply by 1/6 here, so the answer for the leftover millimoles of iron 3 oxide is 29.6 millimoles. We have 3.33 millimoles of iron 3 chloride and 5 millimoles of water being produced. Okay, so this is the end of the table, but let's go back and look at our questions. What's the concentration of Fe? So that's one question. That's left over when all the HCl has reacted. So all that's gone, what's left over? We know that this oxide right here can actually be, can ionize here, and the iron 3 chloride can ionize. Well, alright, I continue to lie to you. I keep trying to tell you that this is going to be soluble, but the iron 3 oxide is actually insoluble in water. Since the acid has been consumed and this is only left in water at this point because of the water present at the end here as a product, this is not going to be ionized. It does react with acid, but it will not ionize in water. Nor will the iron 3 chloride because it's a precipitate here. So if we're asked about the concentration of F3+, then this is going to be 0 molar. The next question is what mass of iron 3 oxide will not be reacted. Essentially, we just need to convert this back to moles and then go to grams. So 0.0296 moles of iron 3 oxide times 1 mole on the bottom here. And the molar mass of that is 159.7 grams. That's going to give us 4.727 grams, but we only can have 3 sig figs, so that's 4.73 grams. Alright, so that was a rough problem there. But yeah, I fixed everything, so this is all perfect right here. And let's continue. A 25 milliliter portion of HCl is titrated with 0.0775 molar NaOH. So we've got the molar or the volume here, and we have the known standard solution. The titration requires exactly 37.46 mils of the standard solution to reach the endpoint, which we're going to assume is approximately equal to the equivalence point here. What's the molarity of the HCl solution? So same thing, NaOH plus HCl yields NaCl plus agua. We know that this is 0.0775 molar, and we know the volume. We know 37.46 milliliters. And we can assume this is millimoles per milliliter. And we could set this up like the before, during, and after equation, but we simply don't need to do that. We just need to do basic stoichiometry. So I'm going to write this a little bit neater. 37.46 milliliters of NaOH is used, and you've got the molarity is 0.775 millimoles of NaOH over 1 milliliter of NaOH. The milliliters cancels out. This is a 1-to-1 mole ratio, so 1 millimole of HCl per 1 millimole of NaOH. The question asks for the molarity of HCl, so yet again we have molarity or moles on top or millimoles on top, so we need to divide by the molarity, by the volume, which is the same thing as multiplying by the inverse. So millimoles per milliliter is going to give us a molarity, which is 0.116 molar. So that's pretty easy. And if you remember, if you have a 1-to-1 mole ratio, in this case we do, you can actually implement the M1V1 equals M2V2 solution or dilution equation. Just making sure you group together the appropriate numbers and you will get exactly the same number. Number 5, a mixture of is prepared by adding 50 mils of 0.2 molar hydrochloric acid to 45 mils of 0.18 molar potassium hydroxide. Is the resulting solution acidic, basic, or neutral? Alright, this seems pretty straightforward. But we're going to have to implement a reaction showing, I like to do my before, during, after, showing what's left over at the end of the reaction. Once we know what's left over, we have to assess the concentration of H pluses and the concentration of OH minuses to see if it's acidic, basic, or neutral. So this is going to take us just a minute here. So I'm going to take my, well, I guess I should write my equation first. HCl plus KOH yields, let's do HOH first, plus KCl. Okay, so I have 50 milliliters of HCl in a molarity of 0.200 molar, and I have 45.00 milliliters, and I have 0.180 molar of KOH, 0 of this and 0 of this. When I multiply these, I'm going to keep my millimoles because I love millimoles. That's 10 millimoles of HCl, and I have 8.1 millimoles of KOH. If I look and I divide by my, this is all 1-to-1 ratio, 8.1 divided by 1 and 10 divided by 1. Here's my LR, so I know that this one needs to run out first. 8.1 millimoles is being subtracted, minus 8.1 millimoles, plus 8.1 millimoles, plus 8.1 millimoles. Alright, so we know the KOH disappears. Then we do our math and we get 1.9 millimoles of HCl left over here. We get water made, 8.1 millimoles, and we get KCl made. Now, KCl does not contribute to our pH at all, because KCl, both of these, this is coming from a strong acid and a strong base, so this is a neutral salt, so this isn't going to sway it either way. Water has both H pluses and OH minuses in it, so this is also neutral, so it's not going to sway it either way. However, you have H plus left from the reactants. It's our excess reagent, so HCl is our excess reagent. So it's definitely going to make our situation acidic. Now, what if I want you to calculate the actual pH? This one just takes a little bit more work. We know that since it's a strong acid, that we will also have 1.90 millimoles of H plus in the solution. But what is the solution made of at this point in terms of volume? It's 50 plus 45, which is 95.0 milliliters. So we take the millimoles divided by the milliliters. That's going to give us our H plus concentration, which is 0.020 molar. This right here is going to now be plugged into our pH, which is negative log of 0.020 molar, which is 1.70 pH. And that should make sense because it's acidic, and we estimated that it would be acidic. So we did a really good job there. And there's only 2 significant figures after the decimal here because of the 2 sig figs that were present in that concentration of H plus. Alright, we are done with this one. I was getting ahead of myself, but go ahead and practice on some of the problems that I've given you to work on, and please let me know if you have any questions. Good luck!